So, welcome to this class on hardware security. Today, we shall be trying to look into a specific block of AES, which we have already been referring as the AES SBox or the sub bytes. So, we shall take a closer look at the AES SBox and try to see a very interesting work about how you can design a compact AES SBox on hardware. So, what we shall be trying to cover several topics in this part. So, we shall be trying to first of all understand in how many ways the AES SBox can be implemented. We shall be trying to look in specific about into the polynomial basis. We have discussed that there are two types of basis like polynomial as well as normal basis. So, in particular we shall be trying to look into polynomial basis and try to see some circuit optimization techniques. We shall be looking into the polynomial inversion circuit in GF2 part of 8, and I shall be talking about some important sub operations, like one of them is scaling and squaring, and we shall be discussing about how we can do optimizations on it. And in particular, right, the main theme of this work would be how what is called as hierarchical decomposition, or where essentially we decompose a field in GF2 power of 8 to a subfield which is a GF2 power of 4 square, and again break up the GF2 power of 4 into GF2 power of 2. So, we basically have a hierarchical way of developing this design, and that is what we shall be trying to understand. And finally, we shall be concluding about with a discussion on how we can do an end-to-end transformation, because at the end of the day we need the input and the output to remain the same as that in the original AES specifications. So, in particular this work will be largely based on this work by D. Canwright, which was published in Chess in 2005, and it is a very interesting work on designing compact SBox for AES. So, just to recapitulate, we already have been discussing about this in our previous classes, that we have already been discussing about field isomorphisms. So, the spirit of this work is based on field isomorphisms. So, the idea is that we have got the field GF2 power of 8 as originally specified in the AES specifications. We try to find out or express it equivalently in GF2 power of 4 square, and then again that is isomorphic to GF2 power of 2 power of 2. The idea is that if you want to do an operation, say finite field inverse in GF2 power of 8, then it is very costly. So, we try to therefore express that or convert that into a field GF2 power of 4 square by applying an isomorphic mapping. Okay. But the idea is that the underlying operations are now done in GF2 power of 4 rather than GF2 power of 8. Okay. So, therefore, the cost in GF2 power of 4 is significantly less compared to GF2 power of 8. Likewise, we try to express GF2 power of 4 in GF2 power of 2 whole power of 2, okay, and therefore, in the subfield GF2 power of 2 the operations are now done. So, therefore, if you consider this, right, GF2 power of 2 is only 2 bits of data. So, therefore, the underlying operations becomes much more simple. Okay. And also, right, since they are isomorphic, you can actually transform this field into GF2 power of 2 power of 2, and you can do your operations in this field in a more efficient manner, and then again you can apply the reverse mapping to get back to GF2 power of 8. Remember that our AES operates in GF2 power of 8. So, we should be able to operate or get the result back in the original field, in that original target field. So, there are different types of mappings we can define, and different types of implementations can also emerge because of them, and they often are guided by the choice of the underlying basis like polynomial basis or normal basis. Okay. So, we already discussed about that here is a quick recap on that. So, there are two types of bases. Okay. So, one is called as a polynomial base and another one is called as a normal base. So, if you take as a like for every extension field like GF2 power of m, there is an irreducible polynomial as we have discussed Px whose degree is m, okay, if the field is GF2 power of m, and let alpha be the root of Px. Okay. So, if alpha is the root of the of Px, then the set 1 alpha alpha square so on till alpha to the power of m minus 1 is called the polynomial base. Okay. So, there are m elements in this base. Okay. So, therefore, we can express any field element as a linear combination of these basis elements. Okay. Likewise, there is also another basis which is called as a normal basis. So, in normal basis again you have Px which is an irreducible polynomial over GF2 power of m, and let alpha be the root of Px. Okay. So, then your set alpha power alpha square, again alpha to the power of 2 power of 2. So, these are all powers of 2 of alpha. Okay. Likewise, you again do m such powers of 2, that means the final result is alpha to the power of 2 to the power of m minus 1. Okay. So, these are called as a normal basis if the m elements are linearly independent. Okay. So, example like for example, g f p power of k, you can actually generalize it to say g f p power of k also. In that case, the normal basis elements will be alpha to the power of p power of 0, alpha to the power of p power of 1, so on till alpha to the power of p power of k minus 1. Okay. So, again there are k. So, since this is k, there are k elements in the normal basis. As a special example which we will be using in our work, for example, consider g f 2 power of 4 square. Okay. In g f 2 power of 4 square, there are two basis elements. Okay. One is alpha and the other one is alpha to the power of 16. Okay. So, that is the essentially like the normal basis of g f 2 power of 4 square. Okay. Likewise, we will be having normal basis for g f 2 power of 2. Okay, and essentially that will be alpha and alpha to the power of 4. Okay. So, we can essentially enumerate the normal basis elements using this idea. Okay. So, therefore, right first, so let us try to first of all kind of address or answer this question, how many ways can you implement the mapping, I mean the AES S box. Okay. So, by using this concept of what is called as the hierarchical decomposition, or it is often also called as tower fields. Okay. So, first consider the mapping from g f 2 power of 8 to g f 2 power of 4 square. Okay. So, this is controlled by the polynomial R y, which is essentially nothing but y squared plus tau y plus mu. Okay. So, this is an irreducible polynomial in g f 2 power of 4 square. Okay. So, now like as we will be discussing, right, for efficiency we choose this tau equal to 1, because you will see that this tau appears in many output equations. Therefore, to make it like efficient, we can actually plug in tau equal to 1. Okay, we fix tau is equal to 1. So, note that we cannot make both mu and tau 1, because if we make both tau and mu 1, then this turns out to be y square plus y plus 1. Okay. And that is actually an irreducible polynomial for g f 2 power of 2. Okay. So, y square plus y plus 1 is an irreducible polynomial for g f 2 power of 2, which is actually a subfield of g f 2 power of 4. Okay. But what we want is that we want that the choice of mu should be such that r y, that is y square plus tau y plus mu. So, if we plug tau equal to 1, y square plus y plus mu is irreducible over g f 2 power of 4. Okay. And if you want to make y square plus y plus mu irreducible over g f 2 power of 4, then mu needs to satisfy, or mu is essentially a root of the irreducible polynomial in g f 2 power of 4. Okay. So, that means, right, if you express mu as a polynomial in the, then it does not factor in the field g f 2 power of 4. Okay. So, there are two irreducible polynomials, right. So, therefore, mu can take 8 possible values. Okay. So, mu can take 8 possible values. You can see that the four roots will come from this equation, x power of 4 plus x power of 3 plus 1, which is an irreducible polynomial of g f 2 power of 4. You can get distinct 4 roots if you solve the pentanomial x to the power of 4 plus x to the power of 3 plus x square plus x plus 1, which is also another irreducible polynomial of a different kind for g f 2 power of 4. Okay. So, therefore, this equation or this polynomial give 4 roots, this polynomial will give 4 roots, and therefore, in total you have got 8 possible values of mu. You can have 8 possible choices for mu. Okay. But note that we have fixed tau as 1, okay, in our implementations. So, likewise, you can actually continue your decomposition in a hierarchical fashion. The field computations in g f 2 power of 4 are performed by expressing the elements now in the composite field g f 2 power of 2. Okay. So, again this is controlled by the modulo polynomial by taking a modulo of the irreducible polynomial s z, where s z is now z squared plus t z plus n. Okay. Note that I have used like y to denote the top field, y means I have used the indeterminate y to denote the top field, that is g f 2 power of 4 square, and I have used the indeterminate z to denote the field g f 2 power of 2 power of 2, okay, g f 2 power of 2 whole power of 2. Okay. So, therefore, here again, right, this is an irreducible polynomial over GF2 power of 2. So, again like we make t equal to 1 like previous case, like when we had previously we made tau 1, now we make t 1, and n is chosen so that, so this capital N is chosen so that it can be the root of the irreducible polynomial x square plus x plus 1 over GF2 power of 2. Okay. So, therefore, right, this equation has got two roots and therefore, n can take two possible values. Okay. So, now we have kind of enumerated how many values mu can take and how many values n can take in order to understand how many such circuits we can realize with them. Okay. So, the circuit complexity will be decided by these constants, that is mu and n, as well as the underlying basis of your implementation, whether you are choosing polynomial basis or whether you are using normal basis. Okay. So, for example, right, if you are using polynomial basis, for each choice of mu, that is suppose I fix mu, then your polynomial r y gets fixed, right, because your r y is y square plus tau y plus mu. So, tau is 1, if I fix mu, then this polynomial gets fixed, and therefore, right, this equation, that is y square plus y plus mu, will have two roots. Okay. Each of these roots can be independently used as the polynomial basis. So, I can choose either the polynomial basis as y 1 comma 1, or I can choose the polynomial the basis as y 2 comma 1, both of them are polynomial basis. But if I want the normal basis, then there are two roots again. Okay. And as we have discussed, the roots will be y and y power of 16, because this field is GF2 power of 4 square. So, this is my normal basis, and both the roots will give me one normal basis. Okay. So, in total we will have three such basis representations. Okay. So, again like thus there are two choices, two polynomial basis and one normal basis, and likewise for each step of the hierarchy, that means when you are going from GF2 power of 8 to GF2 power of 4 square, and likewise from GF2 power of 4 to GF2 power of 2, you essentially have got three basis choices. Okay. So, therefore, now if we totally count the total number of circuit configurations that we are trying to explore here is 8 multiplied by 3. Okay. Okay, that is your the like the top field, that is 8 power of 3, that is 24. Okay. And this is 2 into 3, which is 6. Okay. That is the that is because there are 8 choices of mu and there are 3 choices of basis. So, it is 24 total possible ways. Likewise, for GF2 power of 2, you have got 2 choices for n and you have got 3 basis choices. So, there are 6 such choices. For the smaller more field, right, the smaller field, there is no, there is no variation. So, you just have got one, but you again can have 3 basis choices. So, this is for when you are representing GF2 power of 2 in terms of GF2. Okay. So, you have got 3 such transformations which you are doing, like GF2 power of 8 you are writing as GF2 power of 4 whole square, GF2 power of 4 you are breaking as GF2 power of 2, and GF2 power of 2 you are breaking up as GF2 whole power of 2. So, you are writing it in terms of GF2. Okay. So, so again I am repeating this, you are writing GF2 power of 8 in terms of GF2 power of 4. You are, so here there are, this is the case which is governing that. Likewise, you are expressing GF2 power of 4 in terms of GF2 power of 2, that is this case. Okay. And likewise, you are writing GF2 power of 2 in terms of GF2, and that is this case. Okay. So, totally write the number of cases, this actually should be a product. Okay. So, please replace this by a product. This is multiplication of 8 into 3 into 2 into 3 into 1 into 3, and this totally counts to 432. Okay. So, there are totally 432 possible ways in which we can have circuits, and you can have what we want to kind of explore is this I would say design space. Okay. And we want to see that where are the opportunities of optimization. Okay. So, basically, right, so let us try to look into them one by one. So, first of all, let the irreducible polynomial of an element. So, remember that now we are considering this, we are considering that GF2 power of 8 or an element in GF2 power of 8 has been transformed to an element in GF2 power of 4 square. Okay. So, there my polynomial is Ry, which is y square plus tau y plus mu. Okay. And let an element in the composite field, therefore, so therefore it will look like this gamma 1. So, gamma is an element in this field, and I can write it as gamma 1 y plus gamma 0. Okay. So, this is my polynomial basis way of writing it. I am writing this using the polynomial basis. Okay. So, y is essentially the root of this equation, and I choose one such value of y, and therefore, I can express gamma as gamma 1 y plus gamma 0. Okay. So, this is what we have already discussed in one of our previous classes, how you can write the inverse of gamma, say gamma 1 plus gamma 0's inverse is delta 1 y plus delta 0, and therefore, write delta 1 and delta 0 can be enumerated in this way. Okay. So, this is something that we have already discussed in one of our previous classes. So, I am not repeating that derivation, but I am trying to stress here that tau, for example, appears in both the equations. Okay. And that is essentially what is motivating us to set tau as 1, so that both the equations get simplified. Okay. As tau appears in both the equations, we set it to 1. Okay. So, now if you do that, then you can do some more simplifications. For example, you can write this, for example, if you observe this term, which is gamma 0 square plus gamma 0 gamma 1 plus gamma 1 squared mu. Note that now I can take gamma 0 common from here, and therefore, I can write this as gamma 0 into gamma 0 plus gamma 1 plus mu gamma 1 square. Okay. So, this is again I am taking an inverse. Note that this element is now in GF 2 power of 4. Okay. Likewise, all these multiplications are now in GF 2 power of 4. Okay. So, if you want to describe this in the form of a circuit, this is how it will look like. So, I have got my inputs gamma 1 and gamma 0, gamma 1 is the higher nibble, gamma 0 is the lower nibble, and if I want to say calculate the output delta 1 and delta 0, so then I can just try to understand the relation of this circuit with these equations. Okay. So, first of all, let us start with delta 1. So, delta 1 is nothing but we are computing an inverse of the part which is inside the first parenthesis. So, if you observe here, we take an XOR of gamma 1 and gamma 0. So, this is essentially computing this part gamma 1 plus gamma 0, and then you are multiplying this with gamma 0. So, note that this XOR is in GF 2 power of 4, this multiplication is also in GF 2 power of 4. So, this is where we are using a GF 2 power of 4 multiplier. So, then we are adding this with an output which is mu gamma 1 square. Okay. So, this part, that is mu gamma 1 square, is where I am feeding one input, the input is gamma 1, and this is computing mu gamma square, which is if I feed in gamma 1 as input, the output will be mu gamma 1 square. Okay. So, this mu gamma 1 square is now added with this part, therefore, gamma 0 into gamma 0 plus gamma 1, and then the total part, right, the total essentially this output is fed to the GF 2 power of 4 inversion circuit. So, therefore, I get this inversion, and this inversion is now multiplied with, or has to be multiplied with a component. So, therefore, this, right, essentially if you observe the delta 1 circuit, then I am multiplying this with gamma 1. Okay. So, therefore, if I multiply gamma 1, I get this part which is delta 1, and if I multiply gamma 0 plus gamma 1, that means I just take this part out, and again I multiply with the GF 2 power of 4 multiplier with the output of this inversion circuit, then I get delta 0. Okay. So, this pretty much explains this circuit and shows how it corresponds with these equations. Okay. And note that this operation is something that we will be trying to stress in our talk, that is what we call as scaling. So, this the idea is that this mu is a constant, and therefore, right, when you are trying to implement a circuit where you are multiplying a constant, you do not apply a full blown multiplier, because that will lead to wastage of gates. Rather, you optimize your circuit, and we call that special circuit which multiplies with a constant as a scaling circuit. Okay. In particular, here we actually do a squaring and then scaling. Okay. And therefore, this circuit is what we will be calling as scaling and squaring. Okay. So, therefore, we will first square and then scale, and we will see that why we do that. There is a lot of opportunity of optimization when you consider this circuit. Okay. So, now what we want to observe is that therefore, this brings us to this scaling and squaring operation, and we want to essentially do a scaling and squaring. That means, we want to implement this step mu into gamma square, okay, and we want to see how we can efficiently implement this. Okay. So, the product in GF 2 power of 4 is similarly performed by expressing an elements in GF 2 power of 2. So, therefore, now we are considering the products in GF 2 power of 4. So, if you observe the circuit here, these operations are in GF 2 power of 4. So, now I am expressing, or we are trying to kind of hierarchically go into this circuit, and imagine that this GF 2 power of 4 is now written recursively in terms of GF2 power of 2. Okay. So, therefore, right, this is a 4-bit operation, GF2 power of 2 will again have 2 parts, each of them having 2 bits. Okay. So, totally it will have 4 parts. So, now therefore, you can actually express the product in GF2 power of 4 in a similar way as elements in GF2 power of 2 whole power of 2, and for that, right, consider the product of 2 elements. So, again now we will be using Z as I have discussed here. So, Z is my indeterminate in this field, and therefore, my elements are say gamma and delta, which I want to implement, which I want to multiply. So, gamma is an element in GF2 power of 2 whole power of 2, and when I express gamma as capital gamma 1 Z plus capital gamma 0, then gamma 0 or capital gamma 0 and capital gamma 1 are both elements of GF2 power of 2. Okay. Likewise, your delta, which is another element in GF2 power of 2 whole power of 2, okay, can also be written as capital delta 1 Z plus capital delta 0, and each of these capital delta 0 and capital delta 1 belong to the subfield which is GF2 power of 2. So, now when I am multiplying these two elements, I have to use an irreducible polynomial as usual, and the irreducible polynomial in this case is Sz, which is nothing but Z squared plus Z plus capital N. So, when I am multiplying these two things, you can observe that there will be a kind of term which I will get as Z squared, okay, and therefore, this simplification is a result of the fact that I have replaced Z squared with Z plus N. Okay. So, therefore, the moment I replace Z squared with Z plus N, you can actually verify it, you should be able to get this equation. Okay. So, therefore, I replace Z squared as Z plus N, and essentially this should follow. So, now when I am trying to do a scaling, right, scaling is nothing but a multiplication, but only that the fact is that the one of the multiplication input or one of the multiplication argument is a constant. Okay. So, in this case, my set, like for example, your input is gamma 1 Z plus gamma 0, but you are trying to scale with this input, that is delta 1 Z plus delta 0. Okay. So, therefore, this mu, right, essentially this is nothing but mu, and mu we can actually control. Okay. So, for example, right, as I have said that I can set delta 1, like I have got two inputs, 2 components here, delta 1 and delta 0. Suppose I make delta 0 as 0, that means I set delta 0 equal to 0. Note that I cannot make delta 1 as 0, because if I do delta 1 as 0, then mu cannot make the polynomial Ry irreducible over GF2 power of 4. Okay. So, therefore, I will have some restriction, and with that restriction I can make mu is equal to delta 1 Z. Okay. And we will further choose, as we will see later on, that delta 1 we will make it as n inverse or the inverse of n, or we will make n as delta 1 inverse to simplify the scaling operation. Okay. First, just keep in mind that mu is nothing but delta 1 Z, that means I have set delta 0 to 0. Okay. So, with these inputs, when I am trying to do a scaling and squaring operation, so the choice of n, right. So, therefore, you can observe that the choice of n, when you are trying to essentially, as we have said, that the choice of n also cannot be arbitrary. The choice of n has to be such that it makes this polynomial Sz, which is equal to Z square plus Z plus capital N, irreducible over GF2 power of 2. Okay. So, note that for that purpose n has to be a root of the polynomial Tw, which is again when you are expressing GF2 power of 2 in terms of GF2 whole power of 2. Okay. That means you are expressing it as elements of GF2 now. Okay. So, then the corresponding polynomial is Tw, which is omega squared plus omega plus 1. Okay. And you can easily observe that the roots cannot be 0 here, because if I plug in 0 I get 1, if I plug in 1 I also get 1. So, therefore, 0 and 1 cannot be roots of this equation. Rather, let me denote the roots as n and n plus 1. Note that the sum of the roots, right, of this equation has to be 1, but from the theory of equations. Okay. And let us just symbolically denote one of the roots to be n, and therefore, the correspondingly the other root is n plus 1. Okay. So, depending upon the roots, therefore, the polynomial, so depending on the roots, the chosen for the polynomial basis w comma 1. Okay. That means, you essentially for the lower field you have got the basis as w comma 1. Okay. And therefore, right, either n will be equal to omega or n will be equal to w, or n square will be equal to w. Okay. So, you essentially have got two polynomial basis choices. You can either make n as w or you can make n square as w. Okay. Note that n square will be equal to n plus 1 because like n square plus n plus 1 will be equal to 0. Okay. And note that when you are talking about like these circuits, right, then n to the power of minus 1 is equal to n square. Okay. So, that is equal to n plus 1, that is n to the power of minus 1 is equal to n square, which is equal to n plus 1. Okay. So, these are small like important observations which we will be using in our optimizations in the like in the following discussions. So, these small tweaks, right, will lead to very efficient scaling and squaring circuits. So, therefore, these are something that we need to keep in perspective. Okay. So, note that you can easily verify these things. For example, what you can do is that you can verify these results quite easily. Okay. If you understand the field structure that we have been discussing. Okay. So, now with this background, let us like just let us try to understand this scaling and squaring circuit. So, for example, like when I am trying to do mu gamma square. So, mu gamma square is nothing but mu multiplied with gamma square. So, what is gamma? Gamma is capital gamma 1 z plus gamma 0 and I am doing a whole square on that. Okay. So, that is equal to mu into gamma 1 z plus gamma 0 whole square, and that essentially you can write as gamma 1 square. Again you can write that as z square plus gamma 0 square, but note that you can replace z square as z plus n, and therefore, with that simplification you will get this as your result. Okay. So, now if I substitute mu as delta 1 z, remember delta 0, I mean delta 1 cannot be 0. So, mu is delta 1 z, and as I said that I have plugged in delta 1 as n to the power of minus 1, and I can also write n to the power of minus 1 as n squared z. Okay. And if I do that, then mu gamma square, or essentially this results in, so if I plug in instead of mu I write n squared z. So, I have got n squared z multiplied with gamma 1 squared z plus gamma 0 squared plus n gamma 1 square. Okay. And this turns out to be n square. So, I just take n square and I do an operation here. So, n square multiplied with gamma 1 square, and note that z into z I will get z square. Okay. Plus z, that means z comes here, and then I multiply n square with this part, that is n square into gamma 0 square. Okay. Plus n square into n, that means n cube. Now, n cube becomes 1. Okay. So, therefore, I just get gamma 1 square. Okay. So, therefore, this essentially is equal to writing as n square gamma 1 square z square, which is the first term. So, now let me just conclude this part by discussing about the final effect of these optimizations on scaling and squaring. Okay. So, therefore, scaling and squaring is nothing but calculating mu into gamma squared. Remember that gamma is now denoted as gamma 1 z plus gamma 0, and then I am doing a whole square on that. So, if I do that, I will get gamma 1 square z square plus gamma 0 square. Remember that I am doing in characteristic 2, and then we will replace z square with z plus n. Okay. So, therefore, if you do that, you will get this as your result, and remember that mu, which is with which you are doing the scaling, is a constant, and that is essentially nothing but delta 1 z. Okay. Remember, delta 1 cannot be 0. So, it is some delta 1 z, and this delta 1 is say n to the power of minus 1, as we have taken as a choice. Okay. So, n to the power of minus 1 is again equal to n square, because n to the power of 3 is 1. Okay. You can easily understand this, because n is an element in GF 2 power of 2. Okay. If you do that, right, then there are 4 elements, and therefore, right, you can verify from Fermat's little theorem that you will get n to the power of 3 as 1. Okay. So, therefore, right, you can actually write n to the power of minus 1 z as n squared z. Okay. And therefore, right, it turns out that mu gamma square is nothing but I am writing n squared z, multiplying it with gamma squared, which is gamma 1 squared z plus gamma 0 square plus n gamma 1 square. So, now if I apply n square over this part in the parenthesis, I will get n square gamma 1 square z square plus z multiplied with n square gamma 0 square, where I am multiplying this over this, and then I have got n to the power of 2 into n, which is n cube. Note that n cube is 1. So, I get gamma 1 square. Okay. So, this you can again write as n square gamma 1 square z square plus z into n square gamma 0 square plus gamma 1 square. This is just copying this result. So, this is equal to n squared gamma 1 squared, and now I can write z squared as z plus n. So, I replace z squared with z plus n because I am doing a modulo with z squared plus z plus n plus z into n gamma n squared gamma 0 squared plus gamma 1 squared. So, therefore, now if I just take the coefficients of z and the constant part, then I will have z into n gamma 1 squared plus n squared gamma 0 squared plus gamma 1 squared. Okay. So, note that you can easily verify that I have got n squared, is easy to verify that you have got n square gamma 0 square which comes here, but the other term, that means if I take gamma 1 square, I will get n square plus 1, okay, and n square plus 1 is nothing but n, because n square plus n plus 1 is equal to 0. Okay. So, therefore, right, this is your corresponding operation when you have done scaling and squaring. This is your final result here. I mean, this is the result till this point. So, now if you observe, right, you can see that we have got scalings, there are some intermediate scalings which you are doing. Okay. In order to realize this scaling, hierarchically you are doing another few, you are doing 2 more scalings. For example, here you are doing a scaling with n because you are multiplying with n, okay, and likewise here you are doing a scaling with n square. Okay. And the other operation is, of course, you are doing an addition. So, you are also doing an addition here which you are doing. Okay. So, these operations are now essentially also needs to be tackled and needs to be again implemented. So, these operations can in turn be therefore converted to elements in GF 2 power of 2 whole power of 2 and again computed in the subfield GF 2 power of 2. Okay. So, these operations are in GF 2 power of 4 because you have now successfully decomposed a GF 2 power of 8 operation into GF 2 power of 4. So, therefore, these operations, that is the scaling, the addition, all of them takes place in GF 2 power of 4, but you can also equivalently write GF 2 power of 4 isomorphically in this field GF 2 power of 2 whole power of 2, okay, and therefore, right, you can compute in the subfield now GF 2 power of 2 modulo again S z which is equal to z squared plus z plus n. Okay. So, therefore, right, this is something that we need to essentially again take a look at, and we need to kind of continue about how we can like, or what is the impact of these optimizations on this overall circuit. Okay. And that is what we will take up in the next class. Okay. Thank you.